Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be finishing up our conversation on spontaneity to talk about how Gibbs free energy and thus the favorability of reaction depends upon the concentrations of products and reactant species. So it was easy to kind of see the general dependence of Gibbs free energy on temperature because it's sitting there right there in the equation. However, concentration's a lot more hidden because it turns out it's embedded in that entropy term. Because remember, the entropy tends to end up depending upon the number of molecules present due to that size extensivity. And so as a result, if we have an increase or decrease of concentration, we're looking at this at a relative change in the available entropy of the system. However, since Gibbs free energy does show a concentration dependence, it means we have to, when talking about Gibbs, present a standard state, just like we did for temperature. So for temperature, our standard state was 25 degrees C. For concentration, it depends upon the phase of the material. So if we're talking about gases, we're going to present all our concentrations in pressures. I know this seems a little weird, but if you remember back to the ideal gas law, the pressure is going to be proportional to the concentration. So all gases are assumed to be under 1 bar of pressure at standard state. However, liquids and solids, their concentration really doesn't change that much. And as such, their concentrations are typically given in mole fraction, and we're going to, unless said otherwise, assume a concentration of 1. And for solutions, our standard state concentration is going to be 1 molar. So this means that if I'm going to be looking at how different my Gibbs free energy is from these standard state conditions, I have to have equations that relate on how much my concentration differs from this standard state condition. So not too surprisingly, this change in Gibbs with concentration will show a temperature dependence because it's based on entropy. The rest of the terms should look rather familiar, but now we're using the ideal gas constant instead of the Boltzmann's constant because we're calculating Gibbs as a molar property. So we're using a molar value instead of the energy per molecule. Otherwise, the natural log comes from the same place that we saw it when talking about the number of microstates. We're essentially going to be looking at how much the difference in microstates in between the concentration we're looking at versus our standard state concentration. The difference in between these two should end up informing how much the entropy and thus the Gibbs free energy will deviate from ideal. As a result, we can go ahead and combine this change in Gibbs free energy with our Gibbs free energy at standard state conditions to find a Gibbs free energy for any non-standard state condition. So let's say that I'm trying to determine the Gibbs free energy at 0.1 molar instead of 1 molar. So I can go ahead and find my new Gibbs energy of formation based on my standard state energy formation and this difference in concentration, again, noting a temperature dependence. However, one of the big problems with this equation is that our choice of concentration and its unit does depend upon the phase of matter. So our general one is just going to be the concentration over its standard state, and we do want these to share units to make sure that the whole natural log term is unitless. So this means that if I'm looking at gas phase species, I'm going to report my concentration in pressure over 1 bar. If I'm going to be looking at an aqueous species, I'm going to be presenting the molarity over the standard state molarity of 1 molar. However, it is worth noting that oftentimes this is given as the concentration in brackets, where this bracket term will represent molarity. And we'll talk more about that next time. However, if I'm looking at solids or liquids, most of the time we're going to assume that our concentration really won't change appreciably because solids tend to be always pure. And if I'm looking at liquids, it turns out I have to end up adding a whole lot of solute before I see an appreciable change in my mole fraction. So when we're looking at changes in our free energy with concentration, we're mostly going to be focusing in on gas phase and solute systems. So what we can do is use this knowledge of how the enter the Gibbs changes with concentrations for individual species to figure out how our Gibbs will be concentration dependent for an entire reaction. And we can do this based on the idea that for reaction A goes to B, I can find my Gibbs free energy of reaction based on the Gibbs of my products minus my reactants, accounting for stoichiometry. So when I do this, I can go ahead and insert the relationship of how the Gibbs of my product depends on the standard state Gibbs and this correction with, in this case, pressure, since we're looking at gas-phase species. And then we'll do the exact same thing for reactants. Now what we can do is distribute out these stoichiometric coefficients and then go ahead and collect all our standard state Gibbs and all our concentration dependencies. So from here, we can go ahead and make use of a couple of features of logs. So the first one that we can go ahead and do is make use of the fact that any coefficient out in front of a natural log can be brought up in terms of an exponential of whatever expressions on the inside. So we'll go ahead and perform that relationship for both B and for A. Similarly, we're going to go ahead and simultaneously, we're going to go ahead and combine the difference in our standard state free energies of products and reactants to give, again, a standard state Gibbs free energy of reaction. So now I'm given the Gibbs free energy of a species, of a reaction, is going to be based on the standard state reaction energy and these two concentration dependent terms. So we have our products with a positive sign and our reactants with a negative. It turns out that if you end up subtracting two different natural log terms from each other, that's the same thing as dividing the first term by the second. And so we went ahead and distributed all of this out here. However, there is one you might notice that this equation starts getting a little bit messy. And one of the reasons these equations start getting a little bit out of control is we have to carry along all of these standard state conditions. However, I do want to end up reminding you that standard state is going to be either 1 bar or 1 molar. So for convenience, oftentimes a lot of chemists get real lazy and we drop this term because it's just 1. And so you can go ahead and present the Gibbs free energy of the reaction as the Gibbs free energy at standard state plus this RT term and the natural log of the ratio of the products over the reactants, where you make sure that each product species is in the correct unit, in this case, pressure in bars, and then we raise it to the power of however many of those moles are being produced or consumed. One of the things I do want to make note of is that if you go ahead and try and figure out the units based on this second expression, you'll notice they don't always work out. And that's because we, for convenience, dropped all of the unit corrections with those standard state conditions. Now you'll notice that this particular equation will only work for this particular reaction, and we want a much more general form. So we can go ahead and expand this as the Gibbs free energy for any reaction can be given as the standard state Gibbs free energy plus the gas constant times temperature times the natural log of Q. And this Q is called the reaction quotient. And all this reaction quotient is the ratio of the concentrations of the products over the reactants, again, making sure that our products and our reactants are both raised to whatever power, power of the stoichiometric coefficients, and in the appropriate units. And again, under most circumstances, we're only going to care about gas phase and solute species. So we'll be using just bar and molar. And as again, such, if you're given concentrations in any other units, you should go ahead and convert to bar and molar unless otherwise specified. So let's go ahead and get a little practice on trying to construct these reaction quotients. So we can try and generate a reaction quotient expression for the two following reactions, both of which will have slightly different rules. So for this first reaction, everybody is in the gas phase. So this means that all my concentrations will be given in pressures, but we have some stoichiometric coefficients. So my products will be the pressure of the ammonia, again, squared because I'm producing 2 ammonia molecules. My reactants will go on bottom, and it's going to be the pressure of nitrogen to the first power and the pressure of hydrogen to the third power. Now, again, you'll note that if I do this in the full form, I have to include the standard state conditions for each molecule. Now, again, you'll note that this makes a very complicated equation. So for convenience, you'll often see me drop these standard states to give a much more condensed form. Again, pressure of the products over the pressure of the reactants, including the correct stoichiometric coefficients. Now, the second reaction is always a fun one. CO2 can react with water to make carbonic acid. So this carbonic acid is what gives the tang to most carbonated beverages, because in carbonated beverages, I literally add CO2 to water. Now, this is a very important reaction as not all of the CO2 dissolves, but we can say that both species are present whenever you drink water, carbonated water, because you'll see some bubbles, but you'll also taste some tang. So if we want to find the ratio of these species, we can use the reaction quotient. So in this case, the carbonic acid is an aqueous species, so I'm going to present it in molarity, divided by a 1 molar standard state. My reactant, water, will not show up as it's a liquid, and CO2 will show up as a pressure. However, since it's a reactant, it goes on bottom, and as a result, you can put the standard state pressure on top, or for convenience, drop the standard state conditions, and it'll be the molarity of carbonic acid over the pressure of CO2, gives you the reaction quotient. Now, one of the reasons why these reaction quotients really end up mattering is they will end up dictating whether or not a reaction is favorable or not. Because again, it's going to depend on the ratio of how much products I have and how much reactants. So let's say I have a reaction that is entirely products. Well, in this case, my Q is going to be exceptionally large. If it's all products, it would be infinite because I'd have 0 reactants. And in this case, my delta G will be quite positive because with a large Q value, as it goes to infinity, this term will always dominate no matter what my original starting sign is. So this indicates that a reaction will be no longer favorable. So it turns out you can never make a reaction that goes to completion because there will always be some tendency for the reaction to go in reverse as I drive my Gibbs free energy more and more positive. Conversely, if my reaction is all reactants, then Q is going to be very, very small. And as Q starts approaching 0, which again would be 0 products form, then I'm going to start making an infinitely small number due to that natural log. So this means that if a reaction is all reactants, then I'm going to have a negative delta G, which means that the reaction will proceed forward. So no matter how unfavorable a reaction is, I'm always going to have some products formed. And this is a very important feature. I can never have a reaction that's entirely products or entirely reactants. And we're going to be spending a lot of time this semester on the consequences of this simple relationship. However, this is a complicated idea, so let's go ahead and look at it a little bit more pictorially. So what ends up happening is we know if I'm pure reactants, I'll have a negative delta G and I want to go forward. If I'm all products, I'm going to have a positive delta G and want to go backwards. So as a result, my reaction always wants to go to a point where delta G is equal to 0, which is going to be some point in the middle where Q is less than infinity, but more than 0. So this point is called equilibrium, and it's going to be where both the forward and the reverse reactions are equally favorable. And so depending on the nature of my original starting delta G and the form of my reaction quotient, it can wildly vary where the system will end up. But in general, you can predict the reaction quotient where equilibrium occurs using the delta G. So because equilibrium occurs when delta G equals 0, so if I know my delta G at standard state, I can then go ahead and back out what the reaction quotient will be when the reaction is at equilibrium. This is an incredibly special point, and it's called the equilibrium point. So this is going to be characterized as the equilibrium constant. So this is going to be the point the point when reaction is at equilibrium is going to be when K equals Q. So again, this will only happen for a single value of Q. Q can vary depending on how many products or reactants are present at any given point. The equilibrium constant is a constant. For every given reaction, there is going to be the ideal ratio where you will land. And so we're going to be spending the next several chapters working with these basic ideas of trying to figure out exactly where any given reaction wants to occur, and working with these ideas of how we can play with Gibbs and ratios to figure out what the real world, what real chemical reactions tend to do from any given starting point. So next time, we're going to start diving into more details of aqueous reactions as we'll start combining ideas of concentration with reaction dynamics. Until then, take care.